The James Webb Space Telescope has just detected light from beyond the Dark Ages, a period right after the Big Bang that lasted about 1 billion years, where dense clouds of hydrogen gas blocked out all light, making early galaxies nearly impossible to see. But now, things have changed. Strange sources of light are emerging from these dark ages, and scientists are beginning to question if we've misunderstood the universe all along. This could change everything we know about the cosmos. Using the James Webb Space Telescope, JWST for short, we've cracked the mystery of the dark ages of the universe. And guess what? It turns out there was light during this supposed pitch-black period. Webb has detected Lyman alpha emissions, which are produced when ultraviolet light from young, hot stars interacts with hydrogen gas. But how did this light reach us through the dense hydrogen clouds of the Dark Ages? Researchers believe that the first stars and galaxies created bubbles and channels of ionized hydrogen, forming gaps in the dense gas. These gaps allowed the Lyman alpha emissions to escape and reach us. The Webb telescope is revealing even more incredible details about the early universe, showing us that the first galaxies and stars formed much earlier and on a larger scale than we ever imagined. Thanks to its advanced capabilities, Webb can detect and analyze Lyman alpha rays like never before. Since its launch in 2022, JWST has been showing us a series of incredibly advanced and bright galaxies that existed during the so-called Dark Ages. The fact that we can see these galaxies means there was far more light during this period than we previously thought. And it's not just Lyman alpha emissions. There were other waves of light penetrating the darkness of space. The galaxies discovered so far are unusually large and show signs of extreme star formation rates. This evidence alone paints a radically different picture of the early universe. If there were more stars back then, it means the universe was illuminated and permeable to light much earlier. One of the most groundbreaking discoveries made by the James Webb Space Telescope, JWST, is the identification of 2 high redshift galaxies that existed long before the Dark Ages. These galaxies are so ancient that, theoretically, they should have existed even before the Big Bang. This challenges our previous data and understanding of the universe. These galaxies exhibit numerous properties that contradict existing models of the universe's origin. For example, a supermassive black hole has been found at the center of one of these galaxies, which existed only 400 million years after the Big Bang. Such findings completely challenge our current understanding of the cosmological timescale and our theories of galaxy formation. Lyman alpha galaxies are crucial for studying early galaxy formation and evolution. Lyman alpha emissions are produced by the transition of electrons in hydrogen atoms and are typically found in the ultraviolet spectrum. However, due to the expanding universe, these emissions appear increasingly redshifted, allowing us to capture and study them more effectively. The JWST is ideally suited to capture waves in the red light spectrum. Lyman alpha emissions, LAEs, serve as silent beacons from the early phases of the universe. They enable astronomers to study processes in galaxies that took place just a few 100 million years after the Big Bang, a period thought to mark the formation of the first cosmic structures. LAEs are vital messengers from this era. However, these emissions could also reshape our understanding of the universe. The traditional view posits that after the Big Bang, the universe experienced the Dark Ages, a period devoid of light due to the absence of stars or galaxies. The universe was also too dense for light to pass through. Rionization marked the universe becoming bright and light permeable, and LAEs were believed to play a crucial role in this process. But what if the Dark Ages and rayonization never occurred as previously thought? If so, researchers might have misinterpreted LAEs. Thanks to the JWST's latest discoveries, our understanding is becoming clearer. By studying LAEs, scientists can gain insights into the early galaxies JWST reveals. LAEs provide reliable information about the formation of new stars and galaxies and the behavior of the intergalactic medium during this epoch. By intensively studying LAEs with advanced telescopes, scientists will continue to gather data on star formation rates in early galaxies, helping us piece together this cosmic puzzle. The images from JWST show star-rich and bright galaxies, suggesting that to understand these galaxies, we need every available source of information. The upcoming Vera Rubin Observatory will provide even more clarity in our quest to understand the universe's early days. Currently, we understand that the strength of Lyman alpha emissions is a crucial indicator of new star formation. These emissions originate from star-forming regions that are relatively young. By measuring and analyzing these emissions, scientists can quantify star formation activity in early galaxies and deduce the processes that led to their formation and evolution. The James Webb Space Telescope, JWST, is achieving unprecedented feats by looking further back in time than any telescope before it. It has uncovered impressive examples of Lyman alpha emitters, LAEs, which are now pivotal to astronomical research. One of the most remarkable discoveries is the galaxy GNZ11. Originally identified by the Hubble Space Telescope and later confirmed by JWST, GNZ11 existed around 400 million years after the Big Bang. Initially, researchers thought it might be a measurement error or an anomaly. However, JWST's spectrometers confirmed strong Lyman alpha emissions from GNZ11, indicating intense star formation. This finding has revolutionized our understanding of galaxy formation rates in the early universe. Another significant discovery is MAX 0647JD, a galaxy in an early cluster. Despite its faint appearance and early phase in the universe, JWST observations show strong Lyman alpha emissions, suggesting substantial star formation activity. This is unusual for a faint and small galaxy. Lastly, there's the galaxy EGS 8P7, located around 13.2 billion light-years away. It also exhibits surprisingly strong Lyman alpha emissions, indicating it created bubbles of ionized hydrogen that allowed these emissions to escape. These discoveries challenge the concept of reionization. The JWST has shown us several bright galaxies from this theoretical epoch, but we have yet to find signs of an all-encompassing darkness. This raises questions about our previous understanding of the early universe. Let's take a closer look at the galaxy GNZ11, which existed about 400 million years after the Big Bang. At its center, scientists have identified a supermassive black hole. This discovery raises numerous questions about how such massive objects could form so early in the universe's history. Traditionally, supermassive black holes were thought to form through the collapse of massive stars or the merging of smaller black holes, processes that take billions of years. Therefore, finding such a large black hole at this early stage seems scientifically impossible based on current theories. What does this discovery imply about our old theories and their validity? We need to consider alternative mechanisms for the rapid formation and growth of black holes. One hypothesis is that these black holes gained mass quickly through direct accretion of gas in material-rich regions of the early universe. Other theories suggest previously unknown forms of exotic matter or energy could be responsible for the rapid growth observed. It is astonishing that so few scientists are willing to consider the possibility that the Big Bang might not have occurred or happened much earlier than we thought. Conservative science is trying to reconcile the old world view with new discoveries by proposing explanations for a kind of turbocharged matter formation. Lyman alpha emitters are expected to help in this endeavor. The enormous black hole in GNZ11 suggests that the dynamics and development of these early galaxies were very similar to those of modern galaxies. Other discoveries by Webb also show structures that imply a universe well advanced in its evolution, only a few 100,000 years after the supposed Big Bang. The scientific race is on. Some researchers aim to prove that the Big Bang, dark ages, and cosmic expansion theories are correct, while others use Webb's findings to support alternative ideas.